Welcome to today's Explainer. We're jumping right in to demystify something that literally powers our entire modern world, but, it feels completely invisible. I'm talking about electric potential and voltage. If you've ever looked at a AA battery or stared at a wall outlet and wondered about the hidden physics actually making things happen behind the scenes, well, you are absolutely in the right place.
But before we even think about looking at any formulas, I want you to ask yourself, what exactly is electrical pressure? I mean, we hear buzzwords like voltage or current tossed around all the time, right? But what is the actual physical force that makes our devices wake up and work? To really get it, we need a solid mental model.
Section 1. The mountain analogy. Understanding gravity and electricity. Okay, let's dive into this. To make sense of this invisible world, I want you to imagine you're standing right at the base of a towering mountain, and you've got this super heavy backpack strapped to your shoulders.
To get to the very top, you have to do work against gravity. It's exhausting, right? But as you hike up, that work doesn't just disappear. The higher you climb, the more gravitational potential energy you are banking. If you were to jump off a ledge, and please, don't actually do that, but if you did, all of that stored energy would be instantly released.
Well, electricity works almost exactly the same way. It's like a giant puzzle where the pieces perfectly match. But instead of heavy masses and giant rocky mountains, we're dealing with electrical charges and electric fields. The actual mechanics of climbing and storing energy, they're fundamentally identical. We've just swapped out our sweaty hiker for a tiny electron.
So the crucial point is this idea of electrical pressure. Just like weather patterns, where high-pressure air naturally rushes toward low-pressure air to balance everything out, electrical charges have the exact same tendency. They desperately want to move from a high electric potential to a low electric potential. That intense desire to fall down the electrical mountain, that is electrical pressure.
Section 2, the mathematics, formalizing the analogy. And honestly, it is such a relief because the formula here is actually incredibly simple. It really just summarizes the physical analogy we literally just talked about.
Here it is, V equals W divided by Q, or electric potential equals work divided by charge. Let's break that down. V is our potential, measured in volts. W is the work done, measured in joules. And Q is our charge, measured in coulombs. So it's just telling us how much work is being done per unit of charge. See? Not so bad.
So what is a single volt, practically speaking? Based on that equation, 1 volt is officially defined as 1 joule of energy per 1 coulomb of charge. Boom. That gives our math a clear, concrete foundation. It tells you exactly how much energy is packed into every single coulomb that flows past you.
Let's put that into perspective with a number we see all the time, 12. Think of a standard 12-volt car battery. When you see 12 volts stamped on the side, it simply means every single coulomb of charge leaving that battery is carrying exactly 12 joules of energy out into your circuit. It's kind of like a fleet of delivery trucks, where every single truck leaves the warehouse loaded up with exactly 12 boxes of energy.
Section 3. Potential versus potential energy, making the big distinction. People mix these two terms up all the time, but we can easily separate them using our mountain analogy. Now, what's really interesting to see here is the contrast. On the one hand, electric potential, or V, is a property of the location itself. It's the sheer height of the mountain, and it exists whether you are standing there or not. On the other hand, electric potential energy, or U, is what the specific charge possesses when it's actually at that location. That represents the mass of our hiker. The relationship linking them is simply U equals Q times V. The location provides the potential, sure, but the actual energy only exists when a charge is placed there to experience it.
Section 4. Understanding voltage, potential difference in the real world. Because out in the real world, we rarely care about a single isolated point.
What we actually care about is the potential difference between 2 points, which is exactly what we call voltage. Voltage is this difference in electrical pressure. It's the literal force that shoves electrons through a copper wire so you can light up a bulb or, charge your phone. Think of it as the steepness of the cliff that forces the electrical river to flow.
And the golden rule you absolutely have to remember here is this: no difference in potential equals no flow of charges, period. If there's no high and no low, the electrical pressure is basically zero. Without that difference, your devices simply won't turn on, because the charges just have zero motivation to move.
Section 5, the final spark, summary and takeaways. Let's wrap up this explainer by looking at a quick recap of the fundamental rules we've covered.
Let's move on and see how this builds together into our core takeaways.
First, electric potential is simply the work done per unit of charge. Second, we measure this in volts, which means joules per coulomb. Third, think of the weather. Charges always flow from high potential to low potential. And finally, electric potential is a scalar quantity. It has a magnitude but no physical direction.
So, I want to leave you with this thought. The next time you're walking down the street and you spot a bright yellow high-voltage sign on a fence or a power pole, ask yourself, how much electrical height is waiting to fall? Realize it's not just some generic warning label. It is a literal measurement of incredible, invisible electrical pressure just waiting to do work, waiting to fall. Energy surrounds us everywhere, every single day. Thank you so much for exploring it with me today, and thanks for watching.